get in the habit, when you know a little bit about aging, to think that everything you measure is going to go down with age. That's not true at all.
Most young people, or people lower than 40 now, could expect to have their own lifespan, maximum lifespan, extended by coming advances.
The major hurdle we have in our capacity to extend life deals more with a fear of the unknown than it does with the biological limits of life itself.
Discovering the secret of eternal youth is an age-old wish. Every generation has tried to concoct some magic formula for keeping people young, but none of them have worked. They always failed because we never knew what actually makes us old. But now at last we've begun to unravel the biological mechanisms which cause aging. We may be on the brink of controlling what happens to our bodies over the years. And like Methuselah, who lived nearly a millennium, we may find ourselves living longer than we ever imagined. In this film, we'll meet a little girl who may hold a clue to one of life's most devastating changes: the metamorphosis of strong young bodies into frail old ones, increasingly susceptible to disease and death. We'll look at mice that were put on diets which extended their lives beyond the maximum length normal for their species. And we'll follow a long-term study of people designed to distinguish normal age changes from the diseases we generally associate with age. Do our cells have a limited lifespan, or can they stay alive forever? We'll look at cell studies and at a rare genetic disease called progeria, which seems to mimic the aging process by compressing a lifetime of external and internal changes into less than 2 decades. Experiments in separating chronological time from physiological time in some systems of the body have been successful. This may revolutionize what we think of as old.
I think the oldest I would like to be would be late 80s.
Yeah, I would feel that 70 is an old age.
I'm 69 myself, and I feel like 39.
I'm 35 now, and I think old is when you start to lose your hair.
I'm 71, and I figure old is about 98.
Just what being old is has been the focus of research on aging at Boston's Beth Israel Hospital. Chief of Gerontology, Jack Rowe.
Any approach to answering the question, what is aging, I think should include some statements about what it isn't. What it is an irreversible, inevitable change that occurs over time. It occurs in all organs and has a major influence on the function of the organism. But perhaps even more importantly is what it isn't. There is a highly prevalent view in America that could be described as ageism, like sexism, racism, and sort of an innate negative view of the elderly. We have in our minds a view of what it's like to be old, and it's not a very pretty picture. It's a view of an end-stage, irreversibly ill, irretrievable human being sitting in the corner of a room in a nursing home, staring blankly out the window. There are specific myths that old is dying, that old is sick, that old is poor, that old is senile, that old is sexless and hopeless and helpless. And what we've learned about aging and about the elderly over the last couple decades helped to debunk some of those myths.
Approaching his 100th birthday, Max London is certainly not helpless or hopeless.
Well, I'm 99 now. Next month I'll be 100. And I got 2 sons and a daughter, and I have 10 grandchildren and 6 great-grandchildren. And one just got married, so something else might happen. I'm getting up 7 o'clock in the morning. I get my shave. I make my breakfast. And I'm lighting a cigar, and I'm waiting for my son to pick me up.
For more than 70 years, Max has gone to work every day at the furniture business he established in Quincy, Massachusetts, shortly after he came to the United States in 1909. He still works there 6 days a week.
I'm able to walk, I'm able to come to work, and I talk to people, and I make nice sales every once in a while, and I'm content, I'm happy.
How are you, Max? Glad to see you. How you feeling?
I'm glad to see you
Good.
come in here.
I came in today, Max, to look for a nice reclining chair.
Yes, my dear man, my dear customer, I got everything for you. Come here, I'll show you the recliner. All right?
What accounts for Max's longevity? Genetic inheritance plays a large part in keeping us from dying prematurely. But studies of long-lived people indicate that psychological factors may also be important. Max certainly has a zest for living and a good sense of humor.
This gas is guaranteed that you wouldn't fall through. See now?
Max is a member of a once elite but now growing group. Today, more than 23,000 Americans are over 100, and there are already about 200,000 centenarians throughout the world. Would Max have lived his life differently had he known he'd live for a century?
When you become 70, 80 years old, you say to yourself, if I had known 50 years ago what I know today, it would have been different, but then it's too late. You got to believe in fate. You walk into your own future, either it's good or it's not so good.
Max was lucky. He beat the odds. At the turn of the century, a newborn could expect to live an average of 47 years. If a baby managed to live through infancy, it would find childhood fraught with dangers. Child labor practices and malnutrition killed and crippled many youngsters. Childhood diseases were epidemic in the years before vaccines were developed. Disease also took the lives and sapped the strength of adults in their middle years. Tuberculosis was common. And if illness didn't get you, accidents in the workplace might. Safe working conditions and health benefits for workers were not priority items for employers. Only as these difficult conditions were overcome one by one did life expectancy rise. It took half a century for Americans to achieve an average life expectancy of 68. Today in the United States, men can expect to reach age 70 and women 77. The fastest growing age group in the country is the over 75-year-olds. But the trade-off for eliminating early death has been an increase in chronic illnesses, which show up in later life. They are often incurable and incapacitating.
Well, my biggest problem is that I was a musicologist, and I had to forfeit all my training and all my experience because I lost the use of my fingers. I have no chance of playing the piano again or concertizing, no more. That had done a big job on me because it was a part of my life.
I noticed it when I got pain in my shoulders, pain in my knees. That's when I felt it. I went to the doctor, and he gave me needles to stop the pain. That's how he told me you had arthritis. I never knew what arthritis was. I wished I didn't have it.
Arthritis, cancer, and many diseases we associate with old age can happen to us because our immune systems deteriorate over the years. A look at the way the immune system works makes it clear why age increases the risk of getting these diseases. Defending the body against internal and external threats are two kinds of white blood cells produced in the bone marrow. The B cells attack invaders with antibodies, while the T cells have a variety of jobs. They are called T cells because they get their instructions from the thymus, the master gland of the immune system. By passing through the thymus directly or by being activated by thymic hormones like thymosin, the T cells learn their immune functions. T cells can attack invading bacteria or viruses directly. They also destroy budding cancers. B cells attack invaders with custom-made antibodies. Sometimes they mistake the body's own cells for bacteria. T's help the B's distinguish the real enemy. By puberty, the thymus has begun to shrink. As it shrivels with age, T cells lose their functions, and we become more susceptible to both infectious and autoimmune diseases. Alan Goldstein at George Washington University thinks we may soon be able to compensate for our lost T-cell immunity by artificially supplying thymic hormones. His optimism is based on the extraordinary results of his work with a young Californian named Heather, who was born with a severe immune deficiency. Heather's thymus gland was not functioning. Alan Goldstein.
Heather's immune system is similar in several respects to the immune system of an aging individual, except it's an extreme. The fact that she had no functioning thymus gland really put her at the end point of what occurs naturally as the immune system ages.
Much of Heather's early life was spent in a San Francisco hospital. With no thymic immunity, every viral and fungal infection was a life-threatening situation for her. Her mother recalls those years.
We were told that when Heather was 9 months old that she probably wouldn't live beyond 5 years old. We also were asked at that point in time, did we want to kind of isolate her and keep her away from other children, or were we going to select to let her live a pretty normal life? And that was our choice, is to let her live the normal life as we could.
It was a difficult decision to make because her parents knew what the risks of a normal life might bring.
Well, when I first saw Heather, she was about 5 years old. She was in critical condition. She was literally dying of overwhelming infection. Her thymus gland wasn't functioning, and she had very few T cells, the white blood cells that are produced by the thymus gland, and so she had no immunity. She had no resistance to disease. And they had done everything else that they could in San Francisco, and they felt that her case was hopeless.
At about this time, a thymic hormone called thymosin, which Goldstein had helped discover, was proving successful in test tube experiments with blood samples from Heather and other immune-deficient children. In another experiment, Goldstein was getting positive results with thymosin he used on immune-deficient mice. Would thymosin injections help Heather?
We reasoned that in animals without thymus glands, when we administered thymosin, we could turn on their immune system. We could get their bone marrow cells to mature into functioning white blood cells, functioning T cells that could then carry out their natural immunity. They could provide Heather, as they provided our immunosuppressed mice, with their own natural immunity, and that this immunity could help to eliminate the viral infections and fungal infections which had troubled Heather for most of her life.
A race against time ensued. Goldstein's lab worked around the clock to purify enough thymosin, then made from calf thymus, to supply Heather with the shot she needed before it was too late. It worked. This is Heather 3 years after she began getting thymosin. Her immunity improved tremendously, and she survived a month-long bout of chickenpox, which certainly would have killed her without the injections. For the last 2 years, Heather has been off thymosin because her own T cells seem to have taken over. The thymosin appears to have prodded her immune system into functioning normally.
Well done. Thank you very much.
Today, Heather is a happy 13-year-old. She goes to junior high school and does all the things any teenager would do.
Heather was the very first person to receive thymosin, and her dramatic clinical improvement accelerated the interest and potential of using thymic hormones to manipulate the immune system to raise one's immunity as we age.
Older people suffering from cancer are now getting thymosin injections in several experiments around the country. Researchers hope the thymosin will beef up their immune systems, which have been weakened by the radiation and chemotherapy treatments used to combat their cancer. So far, early results look very promising. Slowing down with age does not have to mean grinding to a halt. Johnny Kelly is 74 years old. He can be seen jogging along the beach at Cape Cod any season of the year. But he's no ordinary jogger. For more than 50 years, Johnny has run in the Boston Marathon.
My best time in the Boston Marathon, I think, was 2 hours and 28 minutes, but I lost the race. And I was, 32, 33 years old at that time. At 54 years of age, I finished fourth in the National Marathon Championship in Yonkers, New York. And that was, everyone said that was amazing. Now, of course, there's thousands and thousands of competitors, and I'm concerned with my time and not my place now.
In 1981, Kelly's time was just over 4 hours. That year, there were 77 runners over 60 years of age. 53 of them finished the 26-mile race. So it seems that age alone is not a reliable indicator for how old people feel. Another myth debunked. Jack Rowe.
How older individuals feel is really a mixture of two kinds of effects. There is the effect of aging, and then the effect of whatever specific diseases they might have. The goal of studies of normal aging is to try to understand how a healthy, fit, old individual is different from a young individual. What are the changes that occur with age, and how we think and act and feel, and how our heart works and our kidney and our liver. And those changes are important because they form the basis for the influence of age on the presentation of a given disease, the symptoms that somebody has when they're sick, and the response that they have to a given medication.
Older people do not use up sugar as efficiently as younger ones do. On standard tests for diabetes, they often seem to be diabetic. But are they really? Harry Buck has volunteered for a test to determine whether this is a normal age change or a sign of disease. Jack Rowe's team is trying to find out whether the inefficiency in metabolizing sugar, or turning it into energy, is the result of a decrease in insulin production or a decrease in insulin's effectiveness.
Morning, Mr. Buck.
Morning.
How are you feeling? Good. How are we doing, Georgia?
Fine.
IV's working all right?
The line's patent. No problem.
Mr. Buck, how does your hand...
First, the effectiveness is checked by giving Harry insulin intravenously.
Okay, and how about these IVs over here?
That's all right.
All right. All right. Pumps seem to be working all right. Ken, how are we doing with the glucose?
Glucoses are stable. Last glucose was 93 at 45 minutes. There'll be another one out in 2.5 minutes.
Then, Harry gets a glass of sugar water to test his own production of insulin.
Okay, Mr. Buck, we'd like you to drink this now, slowly, over 5 minutes, okay? Can you take it with that hand? That's fine. Is that comfortable for you?
Since he is no longer getting insulin infusions, measurements of the level of insulin in his blood will indicate if his body is producing the hormone normally. For the next few hours, frequent blood samples are taken. Results show that old people do produce normal amounts of insulin. But it is less effective because the level of sugar in their blood 2 hours after drinking the sweet solution is higher than what would be considered normal for younger people. Jack Rowe.
This is important for several reasons. Firstly, a blood sugar level which would be diagnostic of diabetes in a young person might be normal in an old person. And this is a good example of how the diagnosis of common diseases is different in old individuals than young individuals. Secondly, since this change in the capacity to metabolize sugar seems to be a characteristic of normal aging, studies of it may provide us with some clues as to the basic underlying mechanisms of the aging process.
The underlying mechanisms of the aging process of his 1955 Chevrolet are no mystery to Wilk Peters, former dean of foreign students at Morgan State College in Baltimore. He spends a lot of time caring for his old car.
I definitely think that people can preserve themselves just as one can a car. My car is 26 years old. It looks new because I've taken care of it. I've kept it in the garage and I don't let it run down. I work on it myself. Oh, I'm an octogenarian, 81 years old, the 17th of this last September. And I feel happy having lived this long and being in as good a shape as I am.
Wilk is in excellent shape, and he checks his health thoroughly every year by undergoing an extensive physical and psychological examination. He does this as part of the Baltimore Longitudinal Study on Aging. Wilk is one of about 1,000 people aged 20 to 100 who participate in this long-term study. It is conducted in Baltimore at the Gerontology Research Center, which is part of the National Institute on Aging. The study is headed by Reuben Andrus.
The Baltimore Longitudinal Study started in 1958, and it was started because of the need to conduct a longitudinal study. A longitudinal study means that you study the same individuals periodically, time after time after time, for a long enough period of time that aging processes can have an effect.
Participants in the Baltimore study are asked to make a lifetime commitment to the project. One of the original volunteers 24 years ago was Les Higby, who began his participation when he was in his early 40s. Les is now 63 years old.
Every 18 months we go to the Gerontology Research Center in Baltimore, and they thump us and prod us for 2.5 days. The tests that we take cover just about every possible part of the human anatomy.
One of the most basic tests is the treadmill test. Heart function and blood pressure are monitored as participants walk a treadmill, which is constantly increasing its speed and slope. Reuben Andrus.
The treadmill test that we do on our subjects is done for two purposes. One is to be able to diagnose coronary heart disease. The other purpose of the test is one of measuring the overall fitness of the individual. We do two tests, essentially, of movement of the arms. In one of the tests, we're simply looking at the strength of the shoulder muscles. And the other test, we look at how well those muscles can do an integrated, coordinated motion, that is, turning an exercise wheel. What we find is that even though strength declines with increasing age, it is true, the ability to do that kind of integrated activity that requires more than just muscles, it requires an intact nervous system and a connection between the nervous system and muscles. The decline in that function is much more striking, and that's a general principle, as a matter of fact, in the physiology of aging, that the more complex the task, the more likely you are to show a decline with age.
Are you ready?
This is a memory test. Loss of memory is one of the most feared aspects of getting old. Results so far from tests on memory and on the time it takes to respond to a stimulus destroy another myth, that we must expect to lose our mental capacity.
College, water, baby.
What we lose is our speed in processing information, not our ability to process it.
That's all I can remember.
Well, what we know is that in some tests, there is very little intellectual decline or cognitive decline with increasing age. With other tests and more complex tests, it is possible to demonstrate some average decline in function, but those declines don't show up until the very late ages. It's very difficult to show any change until you get into the 70s and 80s, and some individuals even there don't show much decline.
The overall picture of how we age still eludes us, but some significant observations have been made in Baltimore. One is that there is an inevitable, if gradual, decline with age in muscle strength, lung capacity, the heart's ability to pump blood, the kidney's efficiency in processing urine, and the speed with which sugar is metabolized. However, despite this decline, we can still function well because we have so much built-in reserve capacity. Another observation is that there is great variation in the rates of aging among different individuals, and even between different organs within the same person. Reuben Andrus.
That alone tells us that when we ultimately understand the nature of aging, we won't be talking about the process of aging. We'll be talking about the processes of aging. It also means that to do something about it, it's going to be somewhat more complex than finding a single magic bullet, which is going to handle all of these problems.
Studies of old people and longitudinal studies like the one in Baltimore are revealing information on how our bodies change with age. But what causes those changes? Today, there are nearly as many theories of aging as there are researchers, and perfectly plausible hypotheses often seem to contradict one another. In the past, this confusion has often characterized the period just before a major scientific breakthrough. Jack Rowe.
Currently, several different theories of aging are being studied. They begin with changes that occur in the center of the cell in the nucleus. And there are other theories that look at changes in other parts of the cell or changes outside the cell that might influence the entire organism. All of these theories have attracted increasing attention over the last several years, and we're now at a point where it's very exciting for gerontologists. The new information that has been identified relating to several of these theories makes us very optimistic that around the corner there is a breakthrough where we will substantially increase our understanding of the aging process and what controls it.
The first solid clue was discovered by Leonard Hayflick, now head of gerontology at the University of Florida. From his work with human cells, he became convinced that aging was not something that just happened with the passage of time. He found it was the result of a prearranged genetic plan. Leonard Hayflick.
Those of us who subscribe to a program theory of aging simply think that age changes are programmed in the way a developing infant is programmed to maturity, in such a way that the program continues beyond maturity to old age, so that there is a, if you will, a purposeful program that dictates changes over time.
His belief in a program theory is based on research he did growing cells in the lab. Before his work, it was thought that normal cells in culture could live forever, and that there was no intrinsic limit to life. That implied that people might also live forever, if the cells in our bodies could be cared for as well as those in lab dishes. But Hayflick's cell cultures, after going through distinctive phases of life, inevitably died.
This flew in the face of the then existing dogma that said that when cells are grown in culture, that if they are ultimately lost or lose their capacity to divide, it's because the investigator didn't know how to grow them properly. A series of experiments that we conducted over a number of years indicated that that dogmatic explanation was in fact untrue, and that cultured normal human and animal cells have, if you will, a clock that dictates the number of doublings that they are able to undergo in culture.
To grow a laboratory culture, a small number of cells are placed in a dish with food and kept in an incubator. A constant supply of food allows them to keep dividing until they have completely covered the bottom of the dish. The culture is then split in two, and each half placed in another dish with food. When the cells have again spread across the bottom, the population is considered to have doubled. Hayflick found that if the cells he cultured were from human embryos, they always died after about 50 doublings. However, if he cultured cells from older people, their cultures consistently died before reaching 50 doublings. In fact, the older the donor, the fewer the number of doublings before the culture died. He also found that cells have memories. Samples of embryonic cells were frozen in liquid nitrogen at different stages of doubling. When they were thawed out, sometimes years later, they seemed to remember where they'd left off and continued doubling until they reached their 50 doubling limit. Is it possible that this maximum of 50 doublings for human cells is a phenomenon of what Hayflick dubs aging under glass? Perhaps when they are in their natural environment in the body, cells can continue dividing beyond the laboratory limit. And what if cells could be kept in a constantly young body? Would they continue to double indefinitely?
One of the key experiments that indicates that normal cells have a limited capacity to replicate and to function, in fact, are experiments that have been done not in cell culture, but in intact animals.
Using young mice, researchers tried to establish whether mammary gland cells could be kept alive indefinitely. Vigorously growing cells were transplanted into a series of young mice all the same age. The cells were transplanted while their host was still young. The transplants grew well and even outlived their original donor. After moving through 7 young mice, however, the cells began to lose their vigor and were showing signs of age. Eventually, they stopped growing altogether. This proved that even in a constantly young environment, cells have a limited capacity to divide. While the mouse experiments proved that cells have a limited lifespan, they also proved that the limit is not reached in the span of an animal's normal lifetime. We don't seem to die because our cells stop dividing. So what reason could there be for programmed deterioration? Leonard Hayflick.
I suppose the most pessimistic view is to say that our cells have a limited capacity to function and to divide to ensure our deaths. I say that because it's interesting to contemplate that aging as we know it, that is the extreme manifestations of aging seen in humans, occurs in fact only in humans and in the animals that we choose to protect, like zoo animals and domestic animals. Aging in its profound manifestations does not occur in animals in the wild.
In the wild, animals don't get a chance to get old. They are usually either culled by predators or die of disease or starvation. Yet when animals are allowed to live out their lifespan, there seems to be a maximum characteristic for each species. Mayflies live out their entire adulthood in a single day. The longest-lived cat managed 28 years. The maximum for elephants is 69, just short of the average lifespan for people in Western nations. The Galapagos tortoise is the longest-lived species. These huge creatures can live for more than a century and a half, and throughout most of their lives they continue to reproduce. Soviet Georgians and other isolated mountain dwellers often live close to the maximum potential lifespan for humans, which is about 114. Maximum lifespan seems to be controlled genetically by some mechanism within the DNA, which makes up genes. DNA is the master molecule which determines what we are and how we function. But our DNA is constantly being bombarded by ultraviolet light, which causes damage. Normally, enzymes rush in to fix the damage. One theory of aging is that there is a breakdown in our repair system. Damaged DNA then sends incorrect instructions to the cells. Receiving the wrong messages causes malfunctions in the cell's activities. Incorrect instructions from DNA can cause genetic diseases like progeria, which distort normal life processes. Jack Rowe.
Progeria is a rare disease in which children appear to suffer a very accelerated aging process. So that although apparently normal at birth, by age 6 or 7, or certainly 10, they appear old, they're gray or have lost their hair, they have wrinkled skin, they have thin bones, they have blood vessels and hearts like very old individuals. And this process might represent, as an accelerated form of aging, an opportunity to study aging and to see in the accelerated situation what we might not see in the normal situation because the changes are too subtle over time.
Aaron Kushner suffered from progeria. Although he was born with the disease, it did not show up right away. His mother recalls the progression.
For us, it's been a very slow process of seeing Aaron grow up. He started out looking like a normal, healthy child with a lot of fat on his body. He had a full head of hair. He was a very happy, alert baby. And this process of his losing his body fat, losing his hair, his joints becoming less movable, and some of the other things now where his heart is not working as well.
Shape of the nose.
Well, facial features.
Yeah.
It's happened very slowly, and we weren't always prepared for the changes that were coming. Actually, it wasn't until Aaron was 3 that we found out that he had progeria, that we knew he had progeria.
That's what Aaron was.
Yes, it was the same day our daughter Ariel was born. The day we found out what it meant, that it was really a fatal condition.
Not much is known about this disease, which occurs once in every 8 million births. It seems to mimic aging internally as well as outwardly. The DNA of children with progeria does not repair itself efficiently, and when cultured, their cells behave like cells taken from old people. But they are children, and they like to do all the things other youngsters do. Aaron Kushner.
My temple has a day camp, and I work there. And I work with 5- and 4-year-old children. And they really have a lot of trouble accepting the fact that I'm 13.
Sometimes it feels funny when people are looking at them. I try to block it. It's just that, it gives me a funny feeling inside, too.
I like to try to do the best I can by myself. And so sometimes Ariel has to suffer because of that.
Their size also makes it difficult for others to relate to them. They may be as small as 5-year-olds when they are almost teenagers. Aaron and his family often talked about aspects of the disease with a progeria researcher at Massachusetts General Hospital, Dorothy Villet.
Well, these patients in general have a very shortened lifespan. They generally are able to survive into the 2nd decade of life. There are some cases that have been reported who have survived till the 3rd decade of life. But in general, they do not survive beyond their teens.
As teenagers, progeric children already suffer from some of the illnesses which afflict old people. They develop stiff joints, heart disease, and shortness of breath.
In March, we got a referral to see a pulmonary specialist. And we went there, and he diagnosed it as some kind of asthma. And he started, which had nothing to do with the basic progeria. And I think that was probably his mistake, assuming that there was nothing to do with progeria, because it turned out I took medication for it for 2 months, and then it turned out that was a misdiagnosis. It was a wrong diagnosis, and what I have is congestive heart failure. So now I have the proper medication, and I'm doing really much better.
I think that even now there is no way that we can stop the process that seems to be going on. I think our only hope, though, is in understanding what is going on and what regulates that. Because once you know how something is regulated, you might be able to change that regulatory force and alter the rate at which a process is occurring. You might be able to slow it down, for instance. But there is no cure, no, because we don't understand the fundamental defect in progeria.
Aaron celebrated his bar mitzvah at Temple Israel, where his father is the rabbi. A year later, 2 days after his 14th birthday, Aaron died. Another clue to the mystery of aging may be found in the lives of Pacific salmon. The journey from the ocean to their upstream spawning grounds requires a tremendous amount of energy. Researchers following these salmon found that once they enter fresh water, their pituitary glands swell up, and the fish produce large amounts of all kinds of hormones. By the time they reach the spawning grounds, their metabolism has become chaotic from the heightened output of hormones. Many of their organs cannot cope with the stress caused by this metabolic upheaval. Not long after spawning, females and males alike succumb to the havoc wreaked throughout their bodies. From sexual maturity to death is a mere 2 weeks for the salmon. This is a sockeye salmon caught in the ocean before it began the upstream journey. This is one caught upstream just before spawning. Loss of calcium has given it a hump. The salmon's face also changes dramatically. Its snout develops a nasty hook. Fungal infections mottle its skin by the time it has completed spawning. This process of deterioration would span nearly 40 years in the life of a human. The combination in the salmon of an enlarged pituitary and accelerated aging have suggested that a similar, if subtler, mechanism causes aging in man. One researcher believes the pituitary in our own brains may be the pacemaker which initiates the aging process. We know the pituitary sends out hormones to trigger growth and turn on puberty. Perhaps it also sends out death hormones, which cause us to age by preventing life-sustaining processes from occurring. Although such hormones have not yet been identified, there is some evidence that they may exist. At the Andrus Gerontological Center in California, Caleb Finch is also looking for a pacemaker which may regulate aging. His search began by examining the female reproductive system, which appears to be linked to age, since there are no old women who still menstruate.
For a long time it had been thought that the ovary was the sole cause of reproductive aging, and the reason was a pretty good one, because at birth in all mammals the ovary has acquired its maximum number of egg cells, and then they're gradually used up. What wasn't realized, and what now is very clear, that at the time cycles cease, there still is a large number of egg cells remaining in the ovary, and this is true of humans as well as of mice and rats.
Finch experimented with mice which no longer experienced the reproductive cycles, called estrus. He thought defective eggs might account for the signal to cease estrus.
The proof that the remaining egg cells in the ovary are still viable is very simple. One can transplant ovaries from old animals into young animals, and the cycles resume, and these egg cells can be shown to have fertility.
Finch took the ovaries from old mice and transplanted them into young ones. Estrus cycles began again, and perfectly healthy litters were born. So if aging ovaries and defective eggs were not controlling estrus, where were the signals coming from? The signal to begin estrus goes from the brain to the ovary, which produces a hormone responsible for maintaining fertility. But with each cycle, the hormone accumulates in the brain, aging it and causing damage. Eventually, the aging brain stops sending the estrus signal. What are the ramifications of unraveling this aging process? Caleb Finch.
My hunch is that in the next 20 to 40 years, we'll have a substantially and solid list of brain aging processes which are controlled or influenced by specific factors. In some cases, it may be possible to intervene to prevent the preconditions for serious deterioration. It may be possible then to live much more of the human life potential in good health and with major capacity.
At 57, Roy Walford is doing all he can to make sure his life will be long and healthy. A researcher at UCLA, he believes the immune system is the pacemaker controlling aging. His experiments are aimed at finding out what controls immunity. Discovering that could make it possible to beat the current biological limits to life.
In my view, we will be successful in extending maximum human lifespan, probably in the next few years or within at least before the close of this century.
He began his investigations by repeating Mackay's classic experiment in extending the maximum lifespan of mice by underfeeding them. The same food was given to 3 groups of genetically identical mice, but the amounts differed. One group was fed daily, a second was fed every other day, and a third control group could eat as much as it wished. This is a mouse which was fed every other day. It seems energetic and healthy, certainly when compared to this tottering, sickly fellow which was fed daily. The control group on unlimited rations had all died by this point in the experiment. The underfed mice in the top cages outlived all the normally fed mice. Roy Walford.
Underfeeding has not only allowed the animals to live their regular maximum lifespan, but has actually extended the maximum lifespan for the mouse species. This is a true retardation of the aging process because it extends maximum lifespan. That would be the same as extending human maximum lifespan, for example, from the present 110 years to, say, 150 years.
These are two of the experimental mice. The one on the bottom has a tumor on its hind leg. The underfed one has not developed any of the tumors, which these mice normally get as they age. Because underfed mice are healthier, Walford thinks the reason underfeeding extends lifespan may be because it delays or prevents damage to the section of the DNA which codes for immunity. Another food-related line of research which interests Walford personally has to do with the free radical theory of aging. As our bodies metabolize food and turn it into energy, chemical reactions release molecules of oxygen and other substances called free radicals. These free radicals can bond with the fats which make up cell membranes. This damages the cell's ability to function. Some of the physical changes we call aging are the result of free radical damage. However, to prevent this, our bodies produce scavenger enzymes called antioxidants. The antioxidants roam the body in search of free radicals and combine with them before any damage is done. But as we get older, we produce less and less of these helpful enzymes. Roy Walford hopes that by supplementing his diet with antioxidants, he will minimize the ravages of age and prevent his body from deteriorating.
Dietary supplements that have antioxidant properties, for example, are vitamin C, vitamin E, the mineral selenium, and then some of the substances present to preserve foods, food preservatives, such as BHT and BHA, which are antioxidant food preservatives, which you find in a small amount in canned goods. But to really get a physiological effect, you have to take larger amounts.
Even those of us who take no active measures to preserve our bodies may have cause for optimism. From his research, Walford believes many age changes can be traced to a super gene, which could eventually be manipulated.
So it looks like the histocompatibility complex or super gene regulates immunity, second messengers, free radical scavengers, and DNA repair. And one notes that these are 3 or 4 of the major theories of aging. So we're able to bring a lot of the theories of aging together into one genetic umbrella, which is the major complex. And I think this is a super gene system which controls aging.
All of the people who will be old in the year 2020 have already been born. By the time these children reach old age, elder citizens could account for more than 15% of America's population. If researchers are successful in finding a way to extend lifespan, that number will grow, creating a much larger proportion of the very old. This could mean a great deal of rethinking about the way our society is structured. Jack Rowe.
Well, governments are increasingly faced with policy decisions about how to handle these previously unimagined numbers of old people. And they're faced with those decisions in 2 areas. One is that there's a very large increase in the number of young old, people 65 to 75, who really aren't sick, are quite fit, but who are being retired, who still are able to make a contribution and want to make a contribution and keep busy. And how are we going to handle that? On the other side of the coin, how are we going to deal with the long-term care needs of this rapidly enlarging old population?
If we manage to extend life, but are not successful in preserving vigor, how will that affect the way we spend those extra years? 5% of today's elderly currently live in nursing homes at an average cost of $16,000 per year per person. By the year 2000, a 50% increase in nursing home residents is expected. Will we be able to afford to maintain even larger numbers of elderly in institutions? Will people want to segregate themselves into old age homes in order to make it easier for others to care for them? A young physician in Boston named Marie Felton has given a lot of thought to alternative types of care for the elderly. She is a founding member of a special medical practice.
The Urban Medical Group is interested in providing primary care to very high-risk elderly people and chronically disabled people. So we've evolved a system of care that approaches their multiple needs by having a team approach that includes nurses, homemaker home health aides, social workers, physical therapists, and also we go out to the location where the elderly people are, to their homes if they can't come to the office, to nursing homes if that's where they end up, daycare centers, health centers, and so on. Mrs. McLaughlin?
Yes, I'll be right
It's
back.
Dr. Felton.
Wait a minute, that's fine.
How are you?
Oh, I'm fine. How are you? I'm so glad that you came.
Oh, you look lovely. Why don't we go into your room?
Yes, I will.
In many instances, this type of care makes an immense difference to the lives of the elderly. We found many elderly people who had been totally isolated for 8 or 9 years in their homes, had never seen a physician, and were getting progressively worse to the point where they were almost ready for nursing home placements. And introducing a homemaker, home health aide, a nurse who comes and visits on a regular basis, has made a tremendous difference, and many of these people can now stay in their homes who would otherwise be in a nursing home. Was Eileen here today, the home health aide? Is she the one who fixed your hair?
8 o'clock this morning she came, she gave a bath, washed my hair, and give me my football, everything.
It takes just $50 a day to maintain people at home. Hospitalization costs $350.
We've taken care of people with multiple illnesses in the home. Pneumonias, bad urinary tract infections, heart attacks, people who need intravenous antibiotics for osteomyelitis, people with strokes. Many of the old people are really afraid of hospitals, and even when they get an illness that probably could be hospitalized or should be hospitalized, they'll often say, no, I want to stay at home. And in fact, we find that when we extend ourselves and are creative in our solutions, we can maintain them at home much cheaper, and they are far more comfortable, and they seem to recover better. I think there really are alternatives for supporting large numbers of old people, but we haven't really even begun to think about them.
An increasing number of old people will mean radical changes in more than just our long-term care system. A breakthrough in preserving vigor would result in a large cohort of physically fit, vital individuals. The Gray Revolution will force changes in our already strained policies of retirement and Social Security. Older workers may have to stay on the job longer because there will not be enough young people in the labor force to support their retirement. On the other hand, young people may have difficulty getting work if jobs do not become available through retirement. The generation gap could turn into a generation war. Perhaps it's time to think more seriously about the many consequences of any extension in lifespan before it becomes reality. How close are we to a breakthrough? Jack Rowe.
Well, it's always difficult to predict where science is going to take us and how likely we are to make that breakthrough, because they're often made by chance. But if you look at the tremendous advances that have been made in studying the biology of aging in the last decade, it becomes a very optimistic view from the point of view of the scientist that we may really begin to understand how to regulate the aging process. What to do with that information once we have it is, of course, another question.
Happy birthday to you. Happy birthday to you. Happy birthday, dear Philip. Happy birthday to you.
Firestone, I want to congratulate you again on your 100th birthday. May you have many, many more with Mrs. Firestone together.
Yeah, thank you.
Arich Hashem.
Lots of love for you.
Thank you.
Lots of love to you. Congratulations, Phil.
Thank you.
Wish you many more birthdays, okay?
Happy birthday to you. And Mazel Tov, Mrs. Firestone. I hope the two of you will be well.
The material on this video cassette is protected by copyright. It is for private use only, and any other use, including copying, reproducing, or performance in public, in whole or in part, is prohibited by law.